In this lesson, you'll learn how to factor polynomials and simplify polynomial quotients by factoring. How does factoring apply to geometry? Suppose the expression 4x squared plus 10x minus 6 represents the area of a rectangle. Factoring can be used to find the possible dimensions of the rectangle. The first thing we always want to look for when we factor is the greatest common factor, which we can see is 2. So if we divide the first term, the second term, and the third term, that's an equivalent expression. If we use the distributive property and multiplied it back out, we get what we started with. And then this is probably the most advanced thing we did with factoring in Algebra 1. We're looking for factors of -6 that are going to give us a sum of 5. So I would pick 6 and -1. So we can rewrite that. So plus 6x minus 3, and that's equivalent to 6 minus 1 is 5. And then we can factor out the greatest common factor, which would be 2x out of the first two terms, and -1 out of the second two terms, carrying the 2 along. And so the greatest common factor of the whole thing inside the parentheses there is x plus 3. And when I take the x plus 3's out, what's left is 2x minus 1. So that's kind of a quick preview of the most complicated factoring we did from Algebra 1. Going way back to middle school, whole numbers are factored using prime numbers. For example, 100 could be written as 2 squared times 5 squared. Many polynomials can also be factored. Their factors, however, are other polynomials. Polynomials that cannot be factored are called prime polynomials. The table summarizes the most common factoring techniques used with polynomials. The first way we learned to factor in Algebra 1 was factoring out the greatest common factor, which we used right here when we factored out the 2. We have also factored using the difference of two squares. The sum or difference of cubes will be new this year. If we have 3 polynomials in a perfect world, it's lovely when we have a perfect square, and we can see that factoring pattern. But in general, we looked for a lot of factors of the constant that give us a sum of the coefficient of x. So in my little quick example there that I just came up with out of the clear blue sky, factors of 12 that gives us a sum of 7 would be 3 and 4. So we'd write x plus 3, x plus 4. We did a lot of those. And for the factor by grouping, I kind of did in our little preview example here, where we had 4 terms, so then we factored out the greatest common factor of the first 2 terms, greatest common factor of the second 2 terms, and lo and behold, by convenience, it happened to leave us with the common factor that we could take out of the whole business. We're going to slow down here and just start by factoring out the greatest common factor. The directions just say factor. Happens to be the greatest common factor of this whole business. I can see I can take a 5 out of all 3 terms. And the lowest exponent for my a's is an a, and the lowest exponent I have for all the b's is a b. So when I divide the first term by 5ab, 10 divided by 5 is 2, a cubed divided by a is a squared, b squared divided by b is b, plus 15 divided by 5 is 3, a squared divided by a is a. The b is gone because b divided by b would be 1, and 1 times anything is what we have there. And same thing here, the 5 divided by 5 is 1, so we don't need to write that down. A divided by a is 1, and so all I have left in my third term is b squared. If I use the distributive property and multiplied this back out, I'd get what I started with. So I know I'm right. Okay, we have 4 terms, so this is a good time for our factor by grouping technique. The greatest common factor for my first 2 terms is x squared. So when I divide that out, I'm going to have x plus 5. My next 2 terms, I'm going to take out -2 because I want to get x plus 5 again. -2x divided by -2 is just x, and negative divided by a negative is positive, and 10 divided by 2 is 5. So the greatest common factor of the whole business now is x plus 5, and when I divide that out, what's left behind is x squared minus 2. And that is not difference of two squares because negative 2 is not a perfect square. So that's all I can do to factor that polynomial. Now, if you were in a testing situation and really wanted to be sure that you're right, you could distribute this out, and we'd have x cubed minus 2x plus 5x squared minus 10. The order is different, but if we rewrote that in descending order of x, we would have the same thing we started with. The FOIL method can help you factor a polynomial into the product of two binomials. Study the following example. If we do first, outer, inner, last using FOIL, we get the product that they have written out there. And then if we just factor out the things that go with the x, we're going to have a d plus bc times the x. Notice that the product of the coefficient of x squared and the constant term is abcd. The product of the two terms in the coefficient of x is also abcd. So we can use that technique to factor polynomials that have a lead coefficient other than 1. So if we take 3 times negative 5, we get negative 15. So we're looking for factors of negative 15 that are going to give us a sum of negative 2. We go with negative 5 and positive 3. So we can rewrite our polynomial as 3y squared minus 5y plus 3y is equivalent to negative 2y minus 5. So the greatest common factor of my first two terms is just y, is all I get. So if I factor out the y, I have 3y minus 5 left. And conveniently, oh look, I can see I have a 3y minus 5 there also. So the greatest common factor of those two terms is just 1. And now I have 3y minus 5 as the greatest common factor of the entire polynomial. So I'm going to bring that out front. And when I divide both sections by that, what's left is y plus 1. For the sake of time, I'm not going to multiply it back out, but again, if you were in a testing situation, you sure could confirm by foiling it back out. I'm going to go to a less complicated example now. The greatest common factor, we only have two terms, so I can take out 5m, it looks like. So what I have left is p squared minus 45 divided by 5 is 9, m divided by m is 1, so that's gone. So now looking at our chart, I only have two terms, so my choices for factoring with two terms is difference of two squares, which p squared is obviously a perfect square, and so is 9. So when we factor difference of two squares, it's square root of first term plus square root of the second term times square root of the first term minus. Okay, I can't help myself. I'm going to multiply this one back out to remind you why that factoring pattern works. So that would be p squared minus 3p plus 3p minus 9. So the difference of two squares factoring pattern works because those middle two terms cancel out. And, oh, by the way, our final answer was 5m times p plus 3, p minus 3. And again, the order does not matter on which is the plus 3 or the minus 3. Now, this is the new factoring pattern that we had not done in Algebra 1, the sum of cubes. So I can see that the cube root of x cubed y cubed, that's going to be my a in the factoring pattern, is going to be x, y. Cube root of 8 is 2, so that's my b. And so I need the first term squared minus the product and the second term squared, and that is factored. Now that chart that we had earlier is really helpful on this one. We can see first of all that we have a difference of squares. So the square root of 64 is 8. Square root of x to the 6 is x cubed, plus square root of y to the 6 is y cubed, and then 8x cubed minus y cubed. Now we're going to get to use the sum and difference of cubes factoring pattern on the same problem. I got really carried away on this one. So cube root of 8 is 2. Cube root of x cubed is x. Plus cube root of y cubed is y. And now we're using the pattern, so then first term squared minus the product and second term squared. Okay, that was lovely. We just did this expression. Guess what? Now this is difference of cubes, so we're still going. So cube root of 8, again we have 2x, only this time it's going to be minus y. And still same pattern, first one squared, minus the product, so minus negative is going to be plus 2xy, and then again plus y squared. In a perfect world, we could write those all in one long chain next to each other, but I didn't want to make it that small. This is one of my favorite algebraic topics because we get to cross things out. If I factor the numerator, so factors of -6 to give me a sum of -1, -3 and +2. Factor the denominator, factors of 10 to give me a sum of 7, 2 and 5. I see I have a plus 2 in the numerator denominator. Anything divided by itself is 1, even an a plus 2. And so my final answer is going to be a minus 3 over a plus 5. Now, in the back of the book, they're going to say x cannot equal -2 or -5, because those two things, if we substitute them into the original expression, would give us division by 0, and we know division by 0 is undefined. In this one lesson, we have looked at every factoring technique we have. You can factor polynomials using greatest common factor, factoring by grouping, or formulas involving the sum and difference of cubes.